So welcome everybody to, thank you. Welcome everybody to this Global Poisson, the Eastern Time session. So today we are very happy to have Hsuan-Yi from Tsinghua University, Taiwan, National Tsinghua University in Taiwan. So he will be speaking on homotopy fiber product of manifolds.
Thank you for the introduction. I'm happy I have this chance to share my research. And I will talk about homotopy fiber product of manifolds. So this is basically about derived differential geometry. And let me start with oversimplified introduction to derived differential geometry. So basically, derived geometry is concerned with space with singularities. And there are algebraic geometry version and the differential geometric version. Algebraic geometry version appeared a little bit earlier than differential geometry version. And for differential geometric version, there are several approaches to this derived differential geometry. And most of the approach based on something called C-infinity rings. And for some reason, we decide to avoid C-infinity rings and develop a different approach. And our approach to this problem is like we basically use vector bundles and sections, geodesics, and some infinity algebras. So let me introduce our approach. And before we start, let me start with a very elementary theory. So basically, I will talk about fiber product. I will try to show you a way to study fiber products. And by fiber product, I just mean the most naive fiber product. Suppose we are given X, Y, Z. There are three manifolds and two smooth maps, F and G's. And we can form the most naive fiber product like this. So this thing is just like say theoretical fiber product. The problem is this space is not necessarily a manifold. It is just a topological space. And we know that if one of the map F over G is a submersion, then this fiber product becomes a manifold. Yeah, so this is like a theory in basic differential geometry course. So let me show you like a couple of examples of fiber products. So first example is intersection of manifolds. Suppose X and Y are submanifolds of a big manifold M. Then the intersection, the set theoretical intersection of X and Y can be considered as the fiber product. I just use the two embedding map and do the fiber product using these two embedding map. Then as a set, it can be identified with a set theoretical intersection. So intersection of some manifolds can be considered as fiber products. Another example is the zero set of functions. So zero set of a function can be considered as the intersection of the graph of these functions and the zeros. So it also can be considered as fiber products, like this kind of fiber product. And the two maps are this map and the zeros. And so these are like two examples, two interesting examples of fiber products. And today I want to show you a way to study fiber product use smooth objects. And our approach is basically resolve this fiber product, which might not be a manifold, by vector bundles and the sections. So this is a kind of outline of the talk. So first of all, I will introduce something we call quasi-smooth derived manifold. And by this, I just mean it is a vector bundle plus a global section. And then I will show you a construction of homotopy fiber product. So as I said, fiber product of manifolds might not be a manifold. So we find a kind of replacement, smooth replacement of fiber product, and that's what I call homotopy fiber product here. And if I have enough time, I will explain the category structure behind these homotopy fiber product things. And then more precisely, I will explain this theory. The category of derived manifolds is a category of vibrant objects. And this structure guarantees we have these homotopy fiber products. And here, by derived manifolds, I mean finite dimensional bundles of curve around infinity one algebras of positive amplitude. Or you can think these as finite dimensional DG manifolds with some degree restrictions on functions. Okay, so what do I mean by quasi-smooth derived manifolds? So the basic idea is pretty naive. So we want to study singular space like zero locus of functions. This might be very singular. So we just replace it by functions. So instead of study this crazy space, we just study these smooth functions and together with a big space. And more formal definitions like this, by quasi-smooth derived manifold, I mean a vector bundle. It is a vector bundle together with a global section of this vector bundle. This thing is a kind of replacement of the zero locus of this section. And between quasi-smooth derived manifold, we have morphisms. And by morphism, I just mean vector bundle maps, which commute with the given sections. That's what I mean by morphism between quasi-smooth derived manifolds. And as we saw at the beginning of the talk, the submersion is particularly important when we talk about fiber product. And here, by submersion, I mean the morphism. When I say a morphism is a submersion, I mean the base map is a submersion of manifolds, and the bundle map, each fiber is surjective. And sometimes I think in the paper we say vibration. Anyway, here I just mean this is what I mean.
Question?
Yes.
So when you say the diagram commutes, there's one diagram with down arrows and another diagram with up arrows, and both of those diagrams commute?
Yes. So okay. Yes. So this, yeah, that's what I mean. Any other questions?
Yeah, I would have a question.
Yes.
So where I don't know, maybe that's going to come on the next slide or so, but where is this derived? Like so far we just have isn't this just a manifold with a vector bundle?
Yeah, it is just manifold with vector bundle.
So not like a vector bundle of a chain complex of vector bundles or so, or?
So you want to see a chain complex? I'm not sure if this is what you are looking for. This kind of stuff.
Okay, yeah. So okay, then you're probably going to get to it. So okay, I'll wait. Thank you.
Any other questions? Okay, then let me continue. So now I just start with a very naive idea, just resolve the singular, the zero locus by this function together with the space. But when we do that, there's a immediate problem. The immediate problem is that there are too many space, too many this kind of thing with same zero locus. So we need a kind of equivalence relations. We need a certain notion of equivalence. And this is what we call weak equivalence. And so to define weak equivalence, I need to define tangent complex. So a point in base manifold is called classical locus or Moria-Gandon locus if it is zero of this section of this given section. And suppose we have a classical locus, we consider the differential of this, the derivative of this section. By that I mean it's just the induced map on tangent space, and then this is a tangent space of the total space, and then I project to the fiber, and this is my differential of section. And then by tangent complex, I mean the two-term complex, this two-term complex. The first term is this tangent space of base manifold at this classical locus. Sorry. So this two-term complex. So the first term is this tangent space of base manifold at the classical locus P, and the second term is this fiber, and the co-boundary map is this differential of this given section. There should be no zero, so there is no zero. And by derived dimension, I mean the Euler characteristic of this tangent complex. In other words, the dimension of base manifold minus the rank of this vector bundle. And a morphism of my quasi-smooth derived manifolds induces a cochain map between tangent complexes. And now I'm ready to define weak equivalence. By weak equivalence, I mean morphism. Weak equivalence is a morphism which induces a bijection on classical loci, and the tangent map is quasi-isomorphism at each classical locus. This is what I mean by weak equivalence. So on the classical locus, it is a bijection, and on tangent space, the tangent complex is quasi-isomorphism. That's what we mean by weak equivalence. So in particular, if we have a weak equivalence between quasi-smooth derived manifold, then they have the same derived dimension. derived dimension is the Euler characteristic of tangent complex. And if the two tangent complex are quasi-isomorphic, then they have same Euler characteristic. And the following example is a nice case. So we say a section is a regular section if this differential is surjective, then we say this is a regular section. If a section is irregular, then the zero locus is a manifold of dimension n minus rank. And this is exactly same as derived dimension. And moreover, the zero, we can consider a manifold as a quasi-simple derived manifold just by considering it as a zero rank vector bundle, And the natural map from this manifold to the given this quasi-smooth derived manifold is a weak equivalence. So in a nice case, it is weak equivalent to the expected manifold. Okay, and here is a kind of functions on this quasi-smooth derived manifold. So given a quasi-smooth derived manifold, by that I mean vector bundle together with a section, we can consider functions on this space, and by that I mean a commutative differential graded algebra. This commutative differential graded algebra, and the degree assignment is like this. So the function part is degree 0, and this wedge one part is degree -1. This is degree -2, and so on and so forth. And this is just contraction. This is contraction with the given section. So this contraction becomes a degree 1 operator, and the square is 0. Yeah, so it becomes a CDGA. And a morphism of the quasi-smooth derived manifold induces a morphism of CDGA between this kind of functions. It's just pullback map. And the weak equivalence I just defined is actually same as the quasi-isomorphism of CDGAs of the functions. So these two are same. Okay. And this is a very quick introduction to quasi-smooth derived manifold. Any questions? Then let me explain what our construction of homotopy fiber products. So homotopy, the idea of homotopy fiber products like this. So recall that a fiber product of manifold might not be a manifold. So this fiber product, suppose X, Y, Z are manifolds, and the arrows are smooth maps. And the fiber product of manifold might not be a manifold. But if one of the maps is a submersion, then the fiber product becomes a manifold. So the idea is like, then I just factorize one of the map. And I just factorize one of the map as a composition of a vibration, a submersion, and a weak equivalence. So in a sense, this Y and the P are same space, and then I just replace I want to replace a map by a submersion. And then I take fiber product, I use this submersion to take fiber product. In this way, I should get a smooth space. And in this idea, the problem is what is this P? How do I get this factorization? So the key is how we can construct this P. So in order to construct this P, we first construct the important case. Construct the P for the diagonal map. This is an important case. And our construction is like this. So here is a diagonal map. I want to factorize this as a composition of weak equivalence and vibrations. So our choice of this space, it is a quasi-smooth derived manifold, so it is a vector bundle together with a section. And our base space is the space of short geodesics, and the total space is a space of certain constant pace in the tangent bundle, and the section is given by derivatives. And the weak equivalence, this morphism is just constant pace, map a point to the constant pace at this point. And the submersion are two evaluation maps. And let me show you more details. Let me explain more about this construction. So what do I mean by these short geodesics and the constant paces? So first of all, we fix a connection. And we fix an open interval, which contains 0, 1. And our PZ is this. This is base manifold, and this is what I call short geodesics. And this is total space, a certain constant pace, and this is the relative. So the base manifold PZ is just the geodesics associated with this connection. So this, we say short geodesics because we just consider we just fix a short interval, fix one interval. And the total space, this total space. So a fiber over this geodesic. So given a geodesics, a fiber over geodesics is pace over this. So we have this is our Z, and the A is a geodesics here, and I have TZ, and then my alpha is here. Alpha is a pace over. Alpha is a pace over A. So alpha is a pace over A. And this is my alpha. Alpha is here. Alpha is pace over A. And it is a pace over A. And such that the connection, the pullback connection applied to alpha is equal to 0. So it is a kind of constant pace with respect to this connection. So in other words, if you trivialize this vector bundle, this pullback vector bundle is a vector bundle over an interval. So it is a trivial vector bundle. You can trivialize it by parallel transport of this connection. If you do that, this alpha becomes a constant pace in that trivialization. Yeah, so that's what I mean by constant pace. So this is my total space. This is my total space. And my section, I call it D here. So the section just maps A to its derivative. Because it is geodesic, geodesic satisfies this geodesic equation. So its derivative is a constant pace. So this is a section. This is a section. And then I have this vectorization diagram. This vectorization diagram. From Z to Z times Z is a diagonal map. And from Z to PZ is a constant pace. And to PZ to Z times Z is the two evaluation map. This is how we get this vectorization of diagonal map. I is a subset of, so I is equal to CD. So I is an open interval, and the 0, 1 closed interval is a subset of I. Because I use the evaluation map at 0 and 1, so I require the open interval, the given open interval. This open interval has 0 and 1. Okay, any other questions? And here is another description of my vectorization. So if you don't like path space, and I can give you another description. So what I said is same as this. So the base, you can think as a base manifold as a tangent bundle. Well, precisely it is actually a neighborhood of zeros in this tangent bundle. And the total space is the pullback bundle, the tangent bundle along the natural projection. This is the total space. And the section just maps, the base space is tangent bundle. So by VP, I mean a tangent vector at P. Map V to BV. That's is there potential issue with completeness? Do you mean the exponential map? So here exponential map is, actually I'm just looking at the neighborhood of zeros where exponential is defined. So I don't look at like very long geodesics, just very short geodesics. So the here, so this is another description of my PZ. Yes, and with this description, the factorization becomes like this. It maps P to 0P. This is the weak equivalence from Z to PZ. And the submersion is given a tangent vector BP. It maps to one, there are two components. The first component is P, the natural projection. And the second component is the exponential map. And because the exponential map is local, local diffeomorphism, so this is submersion. And with this description, you can see it is actually the vector bundle structure becomes very clear, and you can compute. You can really do computation. So I said this is a weak equivalence, and actually it's pretty easy to see. And by weak equivalence, I mean is induced bijection on zero locus. So the zero locus, on classical locus. So the classical locus, the section is here. So classical locus means this B, this is in the fiber, this B is zero, and this B is zero means the first B is also zero. So that means the zero section, the zeros in tangent bundle. And the zeros in tangent bundle is same as Z. The zeros in TZ is same as Z. And you also can compute the tangent complex. The tangent complex like this. This is the tangent complex of Z. So this pi is tangent complex of Z. And this pi is tangent complex of my PZ. And this thing, so this thing, and it's easy to check that this is quasi-isomorphism at each classical locus. So it is indeed weak equivalence. Yes. And this map is a vibration, like what I explained. Basically, it's because the exponential map, and this map is a vibration. Okay, so with this PZ, it's easy to construct the general case with PZ. So basically, general case. So recall that what we want here to do, we want to factorize a given smooth map. Factorize this using quasi-smooth derived manifold. And in this factorization, we should get a summation, and then I use this summation to do fiber product. And the first step was we factorize diagonal map. Now we want to factorize the general map. So for a general map, Y to Z, I just factorize like this. I just take P to be PZ. The PZ is what we got for diagonal map, and times Y, PZ times Y. So more precisely, P is a quasi-smooth derived manifold, and the base manifold is this. Total space is this, and the section is this. So the thing is, when we got PZ, we got summation to Z times Z, and then we use one summation to do this fiber product. So this is a manifold. This is a manifold because the fiber product from TZ to Z is an exponential map. It is a summation. So this map is a summation. So this fiber product becomes a harnessed manifold. Yes. And this space is just a vector bundle with fiber here, fiber tangent space. And just take 10 fiber product. You take fiber product. So I say yes, I already said that. So the base manifold is a manifold because in the previous in the construction of PZ, the map from TZ to Z is an exponential map. There are two maps. One is the natural projection, another, the second one is exponential map. And both of them are submersion. I just use one of them to do this fiber product. So it is a submersion. So fiber product is a manifold. Yeah, this is how we get around the Z to Z it is not, no, I from Z, where is my Z? TZ, so the map is here. So TZ to Z times Z, the map is P and the exponential VP. And this is submersion because the tangent map of this part is the identity. And the tangent map of exponential map is also surjective, so it is submersion. The tangent map is on two. That's what I mean. Is it clear? Yeah, by submersion, I just mean tangent map is on two. Yeah, it is locally. It is locally. It is local. I don't need a complete list. I just take a neighborhood. It is local things. It is local things. Okay, where was I? So I was constructing this P. So this P, I just took fiber product of PZ and Y. And in this way, I can get a quasi-smooth derived manifold together with weak equivalence and submersion. Yes. And you can check it easy that the kernel, the zero set of this section is exactly the graph of the map from Y to Z. So it is same as Y. So this map is a weak equivalence. And now I'm ready to construct the homotopy fiber product manifolds. So now, so as I said, we factorize this part, and then I used then I got a submersion, and then I used this submersion to do fiber product with X. So I just put one more X here. I just did this X fiber product. This part is my P in the previous factorization. So this is my homotopy fiber product. It is a quasi-smooth derived manifold. That means it is a vector bundle together with a section. And the thing is smoothness. So we gather around the singularity by add this TZ. And the TZ, from TZ to this 2Z, one is a natural projection, the other one is exponential map. So both of them are submersion. So when I do this part becomes a smooth manifold, and the other with a submersion from this space to Z. And so the whole fiber product is still a smooth manifold. And the total space is just some vector bundle with fiber tangent space as fiber. And the section is a kind of obvious section. I just put one more V. And it's easy to check that the classical locus of this quasi-smooth derived manifold is the set theoretical fiber product. It is a theoretical fiber product. And the derived dimension is what you might expect. Is the dimension of x plus dimension of y minus dimension z. It is same as the dimension of fiber product in good case. By good case, I mean I just wrote here. So suppose one of the map is already a submersion, then the fiber product is a manifold. It is a manifold, and then we have an inclusion map from this fiber product to the homotopy fiber product I constructed. And this, if this is a submersion, then this map is a weak equivalence. So in good case, this is same as the classical fiber product. Okay, so in here I show you the example I mentioned at the beginning of the talk, the intersection, the case of intersection. So in the beginning of the talk, I said intersection can be considered as fiber product. I just use the two inclusion. Now X, Y are some manifolds of a manifold M. And I have two inclusion maps from X, Y to M. And I just use these two inclusion maps to do fiber product, then I can get set theoretical intersection. And now I just replace fiber product by homotopy fiber product and see what we get. And this is what I call the right intersection here. So by this, I just mean the homotopy fiber product of X and Y. Use the inclusion map. And according to my construction, this is vector bundle together with a section. And my base space is X times Tm times Y. And this space is a space. You can think this space as the space of short geodesics, which start from a point in X and end a point in Y. So it's a short geodesics from X to Y. You can consider this base space as this kind of, you can think this base space as short geodesics from X to Y. And this space can be considered as an open submanifold of the direct product, just consisting the maps, the points, the pair of points which are sufficiently close to the set theoretical intersection. And the fiber over these short geodesics is the constant paces over these short geodesics. Constant pace over these short geodesics. So it is same as tangent space. It's same as a tangent space. And the section is just given by the derivative. The derivative is a section. Oh, I forgot to mention that this TC is just a formal symbol to denote the degree. But we don't have to worry about degree now because we just have one vector bundle now. Okay, so this is my section. So this is a description of my derived intersection. And the classical locus of my derived intersection is the set theoretical intersection. And the derived dimension of this derived intersection is dimension of X plus dimension Y minus dimension M, which is the dimension of intersection in good case. So if X, Y intersect transversally, That's what I mean by good case. Then the intersection becomes a manifold, and there's a natural map from this manifold to my derived intersection, and this map is a weak equivalence. So in good case, this derived intersection is same as the classical intersection. Any questions? Okay, then let me complete the theory. So now I basically finished this quasi-smooth things and the homotopy fiber product of manifolds. And then what's the problem now? So there are some problems. So this homotopy fiber product, what I show you is homotopy fiber product of manifolds. And you can also ask what is homotopy fiber product of derived quasi-smooth derived manifolds. And if you ask that question, then I need even higher structures to answer that questions. So in other words, the category of quasi-smooth derived manifold is not closed on the homotopy fiber product. That's one theoretical question. So this is kind of incomplete in this sense. And another problem is weak equivalence. So I said I need a kind of equivalence relation, but weak equivalence is actually not necessarily invertible. So there's no inverse. So in order to get equivalence, an actual equivalence relation, we actually need some higher structures. And in the previous talk, I used the word quasi-smooth derived manifold. And now I want to remove the word. I want to introduce what is derived manifold. So we just further extend this category of quasi-smooth derived manifold to a even larger category. And that's what we call the category of derived manifolds. And this category of derived manifold doesn't have the two problems I just mentioned. It is a category of fiber objects, and these structures guarantees the existence of homotopy fiber product and these weak equivalences. Can one not use bundles or something similar to realize the inverse? Use bundles. Like stack case. So there are several approaches to these things. So well, I'm not sure which one is your favor. So the equivalence will be something like X, Y, then I have some big space, and then I have some two equivalents like this. And what is XYP? Here I use bundles, and actually I will use bundles of L infinity 1 algebra. You can use digit manifolds, that also works. I think my bundles of L infinity 1 algebra is same as digit manifolds with certain degree restriction. And I try to keep this mentally, so I choose to use bundles. Okay. And then I wanted to say what is category of fiber objects. So this is quite abstract. Let me just go through it quickly. So it is a category together with two subcategories, which is the category of vibration and the category of weak equivalence. In our case, category of this vibration. So that means we have two spatial morphism. One is called vibration, one is weak equivalence. And in our case, vibration is just submersion. And weak equivalence is what I defined. And here are 6 axioms. And maybe the key axiom, I think the most important axiom is this existence of path-based objects. So this is what I construct in the previous sections. The key is I need to find this kind of factorization for diagonal map. And other axioms are like this pullback of vibration exists. So this, I hope this reminds you the basic property of manifold. When you have fiber products, if one of the map is a submersion, then the fiber product is a manifold. This is exactly what it says here. If you have vibration, and the pullback of vibration means the fiber product, and one of the map is vibration. And then in that case, the pullback exists, just says the fiber product is a manifold, so it's still in this category. And this is what this axiom says. So this axiom, I think, is a kind of has this axiom which characterize our situation. And this is what people call category of fiber object. It was introduced by Ken Brown. And in the axiom, I just say the factorized diagonal map. And actually, this is in this guarantees we have factorization for arbitrary morphism. And this is a lemma by Ken Brown in his original paper. And because we have factorization of arbitrary morphism, then our previous idea of homotopy fiber product just works. So in general, in such a category of fiber object, we can just use this thing to get a homotopy fiber product. This PG is the factorized PG is this PX. So I just take ZZ, and this PZ is guaranteed by axiom. And this PZ has vibration to Z times C. So it has two vibration here. So I can do this fiber product. And this exists in this category. And this is homotopy fiber product. This is a general recipe for homotopy fiber product. So this is a kind of general recipe behind the previous construction. This is a general recipe. Okay, and what is my category? So my category is actually a category of derived manifold. By derived manifold, I mean manifold together with a gradient vector bundle is a finite dimensional positively gradient vector bundle. And lambda is not just a section, it is becomes a sequence of bundle maps like this. And it is degree 1 vector bundle maps from K SL to L. And this is curve LNT1 structure. This is a curve LNT1 structure. By that I mean you can use this lambda K to generate a co-derivation, And this co-derivation is called homological. That means QQ is equal to 0. As this is the L infinity axiom. And the morphism of derived manifold now it becomes a morphism of L infinity 1, morphism of L infinity 1 algebra. So that means it is a sequence of map. It is a sequence of map from SKL to L prime. And together it generates a co-algebra morphism. It generates co-algebra morphism from between this SL section. And it commutes, the morphism axiom says it commutes with the L infinity structures. And actually, here is a small remark. The degree restriction implies that we actually have only finite brackets and the finite maps in the morphism. And here are a few the actual equations in the L infinity axioms. So I said curve So the L infinity structure start with 0. The lambda 0 is called curvature because it has this equation, and this is a kind of Bianchi identity. This Bianchi identity, second Bianchi identity. So, and that's why this called curve. This when this lambda 0 is not 0, and this is called curve L infinity. Yeah. And all these other things. So this is a kind of co-boundary map up to some curve, up to some curvature. And this is Jacobi identity up to some homotopy. Yeah. And the easy case, the case of manifold, just take the 0 rank bundle, and if we just have one bundle, then that's the quasi-smooth case I explained. And the weak equivalence and vibration can be defined similarly. So we can we still have this differential of curvature, and it is from Tm to L1, and then we can continue L1 to L2 by the lambda 1, the first bracket, and then the whole thing becomes a cochain complex, and this is a tangent complex. And as before, the derived dimension is the Euler characteristic of this tangent complex, and the morphism induces a cochain map between tangent complexes. So we have tangent map. And weak equivalence just means what I said in the previous section. Induces bijection on classical loci, and the tangent map is quasi-isomorphism for each classical locus. And the vibration means the base map is a submersion. The first map is surjective. So with this structure, weak equivalence and the vibration, now I have a category with two spatial morphism, weak equivalence and vibration. And our main theory is that this category with these two spatial type of morphism is a category of fiber object. This theory guarantees, so that this means we have vectorization. This means we have homotopy fiber product, and we have PZ. We have PZ. We have this vectorization for each diagonal map, and this vectorization we construct this vectorization explicitly by short geodesics. So the previous construction by short geodesics can be generalized. I mean, in our paper, we do that for general case. Yes. And another problem I mentioned in a few pages before is this equivalence problem. So now I can describe when we consider the two derived manifolds are equivalent if they are isomorphic in homotopy category. And that means in this case, that means if there exists the third bit derived manifold and with two trivial vibration onto the two given derived manifold. And this means this is equivalent as isomorphic in homotopy category. Homotopy category means we just input formal inverse of each weak equivalence and complete as a category. Yeah, thank you for your attention.
Okay, so there are some questions. Yeah. There's a question in the chat.
Yes. So let me read. can I combine with higher differential stakes to get definition of higher derived stakes in differential geometry? And the second question is, do I now know how to define geometric structure on derived manifolds? So actually, I don't have very good answer to these two questions. I'm sorry. So yeah, this is interesting questions. Maybe we will study that in the future. So so the first question, I think first question I don't know. Second question, how do I define geometric structure on derived manifold, for example, symplectic structures? So this derived manifold is actually can be considered as DG manifolds. So I think in principle, I can just use the construction of DG manifold. Where is my, here. So here, the function algebra here, I have a CDGA. I have a CDGA. This is my CDGA. So in fact, this derived manifold, I can consider it as a manifold M together with a shift of CDGA like this, like this. Then it becomes a DG manifold, and this becomes a DG manifold. So in principle, the construction for DG manifold you can just apply. Yeah, and there is like shifted the differential forms on gradient manifold, DG manifold, and nice things, right? Any other questions?
So I have a question. It's over there to like I meant like you were saying like so I meant wouldn't your CFO also restrict on this just this one step thingy? Like I guess you were saying like we're saying like weak equivalence is not invertible, but I don't think that's a problem, right? Like you can use some spans, the bi-jet things to still stop this.
You mean the weak equivalence?
I meant like I mean the CFO you were talking about later probably also restrict just to this one step derived manifold. Do you really need to go to infinite length?
Oh, you mean if I have a weak equivalence between quasi-smooth derived manifold, and you think I have, you think this diagram can be in
I just don't see why you I just don't see really necessary to go to more steps to have the CFO. Probably your CFO, the category of fiber object, probably restrict on this one step thingy, wouldn't it?
I don't know. I think it depends on what you need, I guess.
It's like in the stack case, the CFO, the eCFO we have would restrict on all the, like on the 2 group height, the 1 group height in all fixed length, the CFO restrict on that.
Okay.
I think yours probably also restrict on this one length, the 2-step direct manifold.
You mean you mean this
right, category of fiber object, right?
You mean the category of quasi-smooth manifolds is already a category of fiber objects?
That's my guess, and also I asked you explained why it couldn't be, but I think it's okay. Yeah, I think my guess is like they
I
are
don't
your
think, I
CFO
think it's
structure,
necessary.
or
Actually,
you have like an obvious reason not to do it. That's a question.
so I think the problem is this, the main problem is this thing. So the main problem is this factorization. In this factorization, we really need to hire the one more.
But isn't that you spend a lot of time to tell us what is the factorization within the two-step? What do you that thing you call it what quasi
Quasi-smooth. So let me go back. So quasi-smooth here.
quasi-smooth direct manifold, right? Exactly.
So note that here is manifold.
Right.
And here, when we factorize this, we need one more quasi-smooth. We need a
I
vector
see it's
function.
over there. So you always have to go one step higher.
Yeah,
Hmm.
yeah, that's what I mean.
So okay, so that yeah, so for and you cannot find just within this category. Yeah, that's very different than the group Y case. In the group Y case, if it's the one group Y, you can always find factorization just within the one group Y word. You don't have to go higher. Okay. Okay, great. I understand. Thanks.
Okay, are there any other questions? Okay, if not, let's thank Hsuan-Yi. Nice talk.
Thank you.
Thank you. So the next week we'll switch to the Western time. Yeah.